Before any smart environment can make an automated decision, it first has to accurately interpret the physical world. Today, we are building a fully automated alert system from scratch. Step 1 is establishing a threshold alert. We will wire a physical analog dial so that turning it triggers a designated LED to illuminate once it crosses a specific mathematical boundary. Step 2 is auditory. We will construct a secondary alarm that physically escalates in pitch to draw immediate attention to a danger state. You can build this exact workflow using physical microcontrollers on your desk or by using a free browser-based hardware simulator to test your logic digitally. Translating analog physical actions into digital automated responses is the baseline requirement for any functioning Internet of Things environment. We have to start at the component level. Let's clear the workspace. For our first circuit, we need 4 components: our microcontroller, a potentiometer dial, an LED, and a resistor to regulate the current. We will start by supplying power. Connect a wire from the 5-volt pin on your microcontroller directly to the left terminal of the potentiometer. To complete the electrical loop, connect the right terminal of the potentiometer directly to a ground pin. This ensures the current flows safely through the component. This diagram shows the internal resistance of our potentiometer. By connecting the middle wiper pin to the analog A0 port, we establish a data pathway. Turning the dial physically alters the voltage flowing out of that middle pin, sending a variable signal to the microcontroller. To finish the setup, we connect the LED to digital pin 9, routing the negative leg through the resistor to ground. With the analog data routed to an input port and the digital power routed to an output port, the hardware is now physically capable of interpreting variable states. Now we move to the code editor. Before writing our logic loop, we initialize our specific pins and activate the serial monitor, setting the communication baud rate strictly to 9600. As the dial turns, the microcontroller reads that raw analog data and converts the physical voltage into a numerical value. At 0 voltage, the value is 0. At maximum voltage, it hits 1023. This logic flowchart illustrates our primary trigger. We write an if-else statement so that if the incoming potentiometer value reads greater than 500, the system triggers a yes state. If lower, a no state. When writing the action command, capitalization matters. You must use camel case for commands like digital write, with a lowercase d and capital W. A single typo breaks the code sequence. We can now verify the system. As you physically turn the dial, watch the serial monitor values climb. The exact moment the number crosses 500, the physical LED turns on. Drop it to 499 and it turns off. Defining strict numerical thresholds is exactly how raw sensor data gets converted into actionable, automated decisions. Next, let's build out the audio warning. Clear the LED circuit from your workspace and bring in a piezo buzzer component. Wire the negative terminal of the buzzer directly to ground and connect the positive terminal to digital pin 4. We specifically choose pin 4 because it is a standard digital pin. If we used a PWM pin, like pin 3, we would risk signal conflicts with the specific audio frequencies we are about to generate. Back in the code editor, update your setup phase to initialize pin 4 strictly as an output device. This diagram illustrates our for-loop structure. Instead of a single static tone, we write a loop that takes our baseline frequency and incrementally adds 10 on every pass. By feeding that escalating variable into our tone function with a short time delay, we force the hardware to emit a steadily rising pitch. Run the simulation. The code executes, the loop cycles, and you immediately hear a distinct escalating alarm coming from the physical buzzer. By looping variables in the code, static hardware outputs dynamic, time-based events without you having to manually adjust a thing. You now have 2 distinct logic outputs, a mechanical threshold triggering a light and an automated loop escalating an audio alert. These same mechanics drive commercial smart home systems. A thermostat reading analog temperatures to trigger a digital heating system uses this exact logic structure. For your next challenge, take the bonus code snippet provided and try mapping specific audio frequencies to program a recognizable melody, like the Happy Birthday song. Designing your own alerts relies on understanding where physical voltage meets logical code. When you control that specific intersection, you can build systems that react